All right, everybody, welcome back. Ready for another deep dive?
Absolutely. Always ready to dive in.
Well, today we're going deep into the world of superconductivity.
Oh, yeah. Superconductivity. That's a fun one.
It really is. And, honestly, it's one of those topics that feels almost like science fiction.
I agree. It definitely has that futuristic vibe.
But the thing is, it's not science fiction. It's real.
Mm.
And it has the potential to totally change, well, pretty much everything.
It really does. I mean, just imagine a world with, no energy loss in power
Or
grids.
like levitating trains zooming around.
Exactly. And computers that are just mind-blowingly fast, way beyond what we can even imagine right now.
It's pretty wild stuff. So for our listeners who maybe haven't heard much about superconductivity before, could you just give us like the basic definition?
Yeah, sure. So basically, superconductivity is this property that some materials have where below a certain temperature, they have absolutely zero electrical resistance.
Zero. Like none at all.
None at all. It's like a highway with no speed limit for electrons. They just flow freely without any obstacles.
That's pretty amazing. And I know it was discovered over a century ago, right?
Yep. Back in 1911 by a physicist named Heike Kamerlingh Onnes. He was doing experiments with mercury, cooling it down to extremely low temperatures, and bam, he stumbled upon this phenomenon.
So it's been over 100 years of research and development since then. But I think a lot of people still find it kind of mysterious. Like, how does it actually work? What's going on at the atomic level?
Okay, so let's break it down a bit. Every material has what we call a critical temperature. Think of it like a threshold. When you cool a material down below this critical temperature,
Things get weird.
things definitely change.
Mm.
Its electrical resistance completely vanishes, just like that.
So it's kind of like a switch, like flipping it on and off.
Yeah, that's a good way to think about it. It's a sudden and dramatic change in the material's behavior. It's almost like water freezing, right?
Okay, I see where you're going with that.
So, as the temperature drops, water molecules start moving slower and slower, and eventually they lock into this rigid structure that's ice.
Right, totally.
Well, in a superconductor, something similar happens with the electrons. Usually they're kind of bumping around, scattered, creating resistance. But below the critical temperature, they pair up and start moving in this perfectly synchronized way, like a perfectly choreographed dance. No more bumping and jostling, just smooth, effortless flow.
So that's why there's no resistance, because the electrons are basically flowing in perfect harmony.
Exactly. And no resistance means no energy loss as heat, which, as you can imagine, has some pretty mind-blowing implications.
Yeah, no kidding. I mean, think about our power grids today. We lose so much energy just transmitting electricity from power plants to our home.
Exactly. It's a huge amount of wasted energy. But with superconducting power lines, we could potentially eliminate that loss almost entirely.
Wow. So we could power our cities with way less energy than we use now.
Absolutely. We could make our energy systems so much more efficient and sustainable. And think about the environmental impact, less reliance on fossil fuels, fewer emissions.
That's a huge point. It's not just about the technology itself. It's about the bigger picture, the potential to create a cleaner, more sustainable future.
Right. And it's not just about developed countries either. Superconductivity could be a game changer for developing nations, bringing reliable and affordable energy to communities that desperately need it.
That's something I hadn't really considered. It could be a powerful tool for global development and equity. But okay, let's geek out a little bit more. What about some of those other futuristic applications, like those maglev trains?
Oh yeah, the levitating trains. So superconductors are key to making those work because they can create incredibly powerful magnetic
Yeah,
fields.
those magnetic fields basically lift the train off the track.
Exactly. No friction, no wear and tear, just smooth, silent, super fast travel. Some countries are already testing and implementing maglev lines, and the potential is huge. Imagine traveling from New York to LA in just a couple of hours.
Sign me up. And what about computing? I know superconductivity has big implications there too,
Sure,
right?
absolutely. One of the biggest limitations of modern computers is heat. The faster and more powerful we make them, the more heat they generate, and that heat slows them down.
It's like they're overheating, just like a phone or a laptop can overheat.
Exactly. But with superconductors, we could create processors that operate with zero resistance, which means no heat. So we're talking about computers that are not only faster, but fundamentally different in how they work.
So, like, how much faster are we talking about here?
Potentially hundreds or even thousands of times faster than what we have today. It would be a totally new era of computing, revolutionizing everything from scientific research to artificial intelligence.
Wow, it really does feel like we're on the cusp of something incredible. But I have to ask, if superconductivity is so amazing, why isn't it already everywhere? What's holding us back?
Well, there's a catch, and it all comes down to temperature. Right now, most superconductors only work at extremely low temperatures, like close to absolute zero.
How cold is that?
We're talking Netachi 273.15 degrees Celsius, or negative 459.67 degrees Fahrenheit. It's colder than the coldest place on Earth. Maintaining those temperatures is incredibly difficult and expensive. It's like trying to keep a snowball from melting in the middle of the Sahara Desert.
Yeah, that sounds like a major challenge. So the
Yeah.
big goal is to find materials that are superconducting at higher temperatures, right? Ideally at room temperature.
Exactly. That's the holy grail of superconductivity research. And there's another layer of complexity, too. There are actually two types of superconductors, type I and type 2, and they behave differently.
Oh, I didn't realize that. So what's the difference between them?
Type I superconductors are simpler, but they lose their superconductivity pretty easily in the presence of a magnetic field. Type 2, on the other hand, can handle stronger magnetic fields, which is crucial for things like maglev trains. And get this, the whole phenomenon of superconductivity is based on quantum mechanics, the weird and wonderful world of subatomic particles. It's really mind-boggling stuff.
No wonder researchers are so captivated by this, like a whole new frontier of physics and engineering.
It really is, and every new discovery brings us closer to unlocking the full potential of superconductivity.
All right, so let's recap what we've learned today. Superconductivity has the potential to revolutionize pretty much everything, from how we generate and use energy, to how we travel, to how our computers work. It's a game changer, but the big hurdle right now is temperature. Finding materials that exhibit superconductivity at practical temperatures, that's the key.
Couldn't have said it better myself.
So here's something for all of you listening to think about. Imagine you're leading a team of scientists and engineers working on superconductivity. What would you prioritize? Would you focus on developing clean energy solutions to combat climate change? Or maybe you'd pour all your resources into building those super-fast computers to push the boundaries of artificial intelligence. Or perhaps you'd be obsessed with creating a world of high-speed transportation with maglev trains crisscrossing the globe. It's a big decision with potentially world-changing consequences. So what would you choose?
That's definitely something to ponder.
It really is. And it just goes to show how powerful and impactful this seemingly obscure phenomenon called superconductivity really is. Thanks for joining us on this deep dive, and we'll catch you next time for another exploration of the cutting edge of science and technology.
Until next time.
See ya.